Hello, this is Kerry Schutz with MathWorks, and in this video I'm going to show how to bring S-parameters into Simulink as circuit elements. So again, this is our goal. We want to start with a touchstone file, and we want to import that, instantiate that into Simulink as a circuit element. And we're going to be using a block from Simscape Electrical to do that, and an S-parameter rational fit block. So what's motivating this is the use case we see at the bottom, where we want to bring these S-parameters into Simulink and simulate them along with other parts of the system. So we may want to cascade multiple S-parameter objects. We may want to connect and interface S-parameter blocks or device under test to other circuits, other active or passive circuit elements in the system to build a larger system. So what we're not trying to do necessarily is what's in the upper right, and that's take the S-parameter file and just pick out a particular S-parameter, say S21, and model that as a unidirectional transfer function without any type of loading impact, or no reflections, no loading modeled. So we can certainly do this, or we can satisfy this particular use case where we extract a particular transfer function or frequency response and do a fit to it and model it in Simulink, but that's not our goal today. We want to model this superset of transfer functions, including loading and reflections. So we're going to bring it in as a circuit element. We're also not trying to do analog circuit synthesis. This is what you would say is strictly a mathematical exercise when we take the S-parameter file and convert it to an S-parameter circuit element. So we'll be doing a fit on that object, and we're modeling it as a set of poles and residues and direct terms. What we're not trying to do is map it to a particular RLC circuit structure. So where do we start this exercise? Well, anytime you're starting to test out a new methodology, you want to start with a trusted set of data. And so one option would be just take a trusted set of S-parameters you have and attempt to model those back in Simulink so that when you're done, you know that what the right answer is. You know that the model is matching the data. I'm going to take one step back in this exercise and start with a well-understood analog circuit. Then from that circuit, I'm going to derive and or measure the S-parameters, and then those S-parameters will serve as the input or the starting point to model them in Simulink. So the reason for that is that I'd like to know the right answer before I begin. Anytime I'm testing out a new methodology, I want to minimize uncertainty as much as possible. So this allows me to kind of take a baby steps approach to trying out this new technique where I say I trust these S-parameters, I know they're good, they're stable, they're causal, I know that what the response looks like. So when I extract a model from them and model it in Simulink, that I know that it's doing the right thing. So again, I'm going to start with this known analog circuit. This is going to be, in this case, a ladder LLC filter that's implementing an elliptic low-pass filter. I'm going to derive the S-parameters, and I'll show you how I do that in a bit. Then using those S-parameters, I'm going to do a rational fit on them to get the poles and the residues. Then I'm going to instantiate this S-parameter block that's part of Simscape Electrical in Simulink, and that rational fit object will be the input to that block. And then I'll simulate the original circuit, in this case, this LLC low-pass filter, against the S-parameter implementation of it. See how close they are. So again, we're starting with this well-understood circuit, the elliptic low-pass filter. I mention here a few ways that I've shown in past videos on how you can get S-parameters from a Simscape circuit using either a measurement-based approach or a linear analysis-based approach. And there are a couple of videos. I provided the link to my playlist and then the name of a couple of videos on that topic. Now what I'm going to show today is yet a third technique, and that third technique involves using RF Toolbox to describe the circuit. First, I'm going to describe this LLC filter using text, using MATLAB functions from the RF Toolbox, where I add the circuit components, I describe the ports, and then I extract the S-parameters from said circuit object and the variable name SP_LPF, S-parameters low-pass filter, And then using that, there's different methods I can apply to that S-parameter object, like RF plot. And then I'll give me, if it's 2-port, it'll give me the 4 plots for S11, S21, S12, and S22. And that's what you see in the lower right. And this S-parameter object, of course, has certain properties, which you can see over here in the lower left. Once you have the S-parameter object, that will now serve as the input to the fitting process. So I'm going to be calling the rational function from the RF Toolbox. I'll pass along the name of that S-parameter object along with the frequencies over which I'm doing the fit. And then there's a few extra parameters, fitting parameters that you can tweak associated with rational. One of them I used here was called tends to 0. It defaults to true. I set it to false. I got a better fit that way. And then there's a tolerance which defaults to 40, which I just left at the original tolerance value, the fitting tolerance. And there's a few more parameters. I think there's a total of 8 or 9 different parameters that you can tweak or tune associated with rational. Once you do the rational fit, you can then plot the results of the fit against the original S-parameter data to make sure it's a good fit. The rational object will tell you how many ports, how many poles, the residues, whether there's a direct term involved, and the error associated with the fit. And then if you want an app-based approach and you have access to SerDes Toolbox, there's an S-parameter fitter app, so it's a point-and-click approach as opposed to a programmatic fitting approach, where you can specify the S-parameter file and some other fitting parameters via the graphical user interface or the app, and then let it do its job. All right, and of course, the approach I've shown here with this LLC filter, this low-pass filter, is a pretty simple getting started example. But of course, this rational approach I'm showing applies to channels of arbitrary complexity and port numbers. So here I'm showing a channel in the upper left that is highly reflective, 2-port example, and then over here I'm showing a 4-port example where you can see there's lots of dynamics. You see it's generally a low-pass characteristic on the through channels, and then you see the reflective channels have a lot of dynamics, a lot of reflections. So once you have the S-parameter object, the fit object on the S-parameter. So you've got the S-parameters, you've done the fit. Now you can supply that fit to the S-parameter circuit element block. In the block, you would look under Simscape Electrical, passive components. You'll find this block called S-parameter rational fit. Here I renamed it S-parameter elements, but it's the same block. Again, it was introduced in R2024B. You supply the name of your rational fit model to it, along with a reference impedance, and then it is going to implement that back in the time domain. So what happens under the hood of the S-parameter block? So again, you've already supplied the fit object to it. What it's going to do again is convert that to a series of blocks and port connections to implement in the time domain. So if you were to look under the mask of that block, you would see these 3 blocks interconnected, 2 kind of port handling blocks, port selector, and then the rational fit block. If you were to look under the rational fit block mask, you would see a bunch of matrices specified. Again, this was all done for the user, so at the very top level of the model, all you had to do was specify the rational fit object name, RFM. Underneath, it would do a lot of math and compute all these matrices for you. So as far as the way this actually gets implemented, this is not the literal implementation shown on this slide, but it's effectively what it's doing. So at least for an S2P, you would have 4 transfer functions. You would have your input to port 1, reflection back out of port 1, and you have, like your through. Here you'd have your input to port 1, output on port 2, S21, and so on. You'd have your 4 directions or 4 combinations of transfer functions. Again, those are computed based on that rational fit model you provided and is described in these matrices. And then there are, of course, the S-parameter equations that describe the interrelationships between these different transfer functions, like B1. Let's see, where's B1 in this diagram? B1 here, the S-parameter equation equals S11 times A1 plus S12 times A2. Those equations are effectively implemented by this block diagram, where you can see the different parts where we're got controlled voltage sources, we're measuring currents, and we are then from those we are computing these forward and reflected terms. Okay, and then if you look underneath the transfer function blocks, you'll see a series or a parallel connection of transfer functions. These are like biquad structures in parallel that are summed along with the direct term and a delay term. And that's, now those are unidirectional in nature, but it becomes bidirectional in nature via the S-parameter equations. Again, this is not the literal implementation of what happens in the Simscape use case here, but it's effectively what it's doing under the hood. Once you have the S-parameter rational fit object block in Simulink, you can connect it to other circuit elements and simulate it as a larger system. Here I'm showing I simulated my original elliptic low-pass filter implemented out of discretes and simulated against the rational fit implementation, and just make sure their step responses overlaid nicely and make sure they're working well. You could do the same thing using a frequency response approach, or think of it like a network analyzer-based measurement, where I drive each port with a broadband signal, in this case random noise, and then I measure the response. And in that case, that would be more like an S21 measurement compared side-by-side magnitude and phase. And then if you were wondering how that measurement was done in Simulink, I've got a video just on that very topic as well. It goes under the hood of the transfer function estimator block. And of course, the ultimate goal, the motivating circumstance for bringing S-parameters in is, of course, most likely to model S-parameters as a part of a larger system where you may cascade S-parameters, or you will likely connect them to other circuit elements. Perhaps you've got some type of equalization on a channel you would like to try, so an analog equalization circuits connected to your channel that you could simulate now as one larger system in Simulink. So again, the process is really a three-step process. You start with your S-parameters, you perform a rational fit on them to get the mathematical or PO residue model. Then you bring in your Simscape Electrical S-parameter rational fit block and supply that rational fit S-parameter a rational fit model to it. Then you would simulate and confirm that your rational fit implementation matches well with the original S-parameter measurements. Now you can, of course, also take and use these results of your rational fit over in MATLAB as well, not just Simulink. So you do your rational fit, as I showed before. You're going to get this variable, this rational fit block, our variable RFM, and then there are various methods or functions you can apply to that rational fit object, one of them being ZPK for zero pole gain, and that will give you back your zeros, your poles, and your gain, also your DC gain term as well, from that rational fit model description. And if you do methods on that rational fit variable or object, you can get all the other methods like convert it to ABCD form, get the impulse response, test for passivity, get the step response, is it causal, get the time response, the frequency response, test for passivity, write out a Verilog A file, generate a SPICE model, and of course get the zero pole gain description as well. Okay, enough of the slides. How about we get into an actual demo? Our goal is to get into Simulink, but we're going to start again by essentially synthesizing our device under test that's going to lead to our create our S-parameters. So we're going to start with the design, which is an LLC, or ladder structure of elliptic low-pass filter that was taken from this particular reference, Handbook of Filter Synthesis. The LC vector is described accordingly. By this vector, I'm going to pass that in as an input to a particular function, which is going to leverage RF Toolbox to create this filter and extract the S-parameters. So we're going to pass in that LC vector. We're going to go all the way down to the bottom of this file, and what you're going to see is that we pass in the LC vector, and then we compute a few additional components. In addition to the the LLCs you saw in the circuit diagram earlier, there's also going to be some series R's as well associated with each inductance. So L1 is going to have R1, L2 is going to have R2, finally down to L5 is going to have R5. And from that, now we're going to actually build up the circuit using RF Toolbox, the circuit object in particular. And you see that we're going to create an inductor that's going to go between nodes 1 and 2, a resistor between nodes 2 and 3, an inductor between nodes 3 and 4, and so on, all the way down until we get to the last component. And then we are going to then define 2 ports, port between 1 and ground and 11 and ground. And then we're going to extract the S-parameters from that. We'll store those in a variable called SP_LPF for S-parameter low-pass filter. That's the return. We're going to return that variable to our script. And then we can plot out things like S21 from that S-parameter object or any other S-parameter combination. We can save those results away to an S-parameter file. We can write out touchstone files of a particular format. Optionally, I used Symbolic Math Toolbox to derive the transfer function of this circuit as well. So I described the inductances, the capacitances, the resistances associated with the inductances, as well as the source and load impedances. And then I used cascaded transfer parameters, network parameters to describe the overall relationship between the input and the output. I extracted V2 over V1 and did frequency response analysis on it to plot out the step response, the phase response, and the magnitude response of it. And then we get to the meat, then we finally get to what I'll say is really step 1 for most people, and that is if you have the S-parameters, now they serve as the input to the rational function. You notice there's a number of extra parameters I included in the script just to give you a feel for what the different parameters that you can tweak or tune associated with rational are. The ones I showed in the PowerPoint were just the tolerance, which is the default of -40 dB, and tends to 0 false. That actually did lead to a better fit. By default, it is true. And then you can say the max number of poles in the fit, the noise floor, whether you want to share poles or not, things like that you can also specify. But for the most part, the defaults do pretty well. This returned a rational fit model or some variable which holds the rational fit. And then you can do things like get the frequency response from that fit. There's a number of functions or methods that I showed earlier in the slides that you can apply to a rational fit object. And one of the things I did was I went through and I got the frequency response from each of the fits, like S11, S22, S12, S21, etc. And then I plotted those against the original S-parameter data just to make sure my fit was doing was accurate. Once I had that, then I could bring that fit over into my Simulink model, and then I could say, okay, here's my original model described using Simscape discrete elements, passives. Here is my S-parameter rational fit block from Simscape Electrical, where I described or specified the rational fit object name, and then connect circuit components to it. In this case, it's just simple input and output or source and load impedances, connect some type of source, excite the system, and then compare the 2 responses. I can do that up here. I'll just hit play in the model, and we'll let it go. All right, now it's starting to run. I've called up my magnitude and phase plots, and it's starting to run here. Let's see, up to it's just a few microseconds. I got to collect enough data to do an actual transfer function and magnitude response plot. There it goes. It's got magnitude response on top, phase response on bottom. It is overlaying the two, so it's overlaying the discrete implementation version against the S-parameter block. That's why you see the 2 colors up here, yellow and blue. If I turn off one, since they're overlaid perfectly, you can see that the other one lies right on top of it. Same with the magnitude and phase. If I turn off one of them, you'll see the other. In this case, the yellow is the discrete implementation. The blue is the S-parameter rational fit implementation, and they're very, very close to lying exactly on top of each other. So that's pretty convincing that the two, the fit is good, and the implementation of the fit via the S-parameter rational fit block is also good. So again, back to the fitting process itself, if you do have access to RF Toolbox, there is an S-parameter fitter app where you can specify the name of your S-parameter file, and then it will return an S-parameter fit and also do the plots for you, so you can see how well the fit is performing. That's certainly another option at your disposal. But even if you don't have that, you can still write a script on your own, as I did here, and you can just take the results of the rational fit, the results of the rational fit, in this case is RFM, and you can get the frequency responses from it, and then you can overlay, again, you know, like the 20 log 10 of the fit against the data, against the S-parameter data. So that way you can compare and contrast in the frequency domain the magnitude and phase responses against each other. Okay, I hope that was helpful. Signing off until next time.